Okay, this is homework 1, part D. So, in this problem, if we are given a spherical shell, such as this one, with a inner radius of 1 meter and outer radius of 2 meters, and the inner surface is at 100 degrees Celsius, while the outer surface is 0 degrees Celsius, how can we find at the temperature of the midpoint at radius equals 1.5 meters, given that we have uniform thermal conductivity? Okay, so to begin, we'll first need to get into units of our temperature. So to do that, we'll start with Fourier's law, which, as we know, is our heat flux is equal to our negative thermal conductivity times our area times our temperature gradient. It's change in temperature with respect to position. Okay, so applying that equation to our problem here, we would get our heat flux is equal to our negative thermal conductivity times our area, which in this case is 4 pi r squared, times our temperature gradient, which will be our change in temperature with respect to the change in radius. Okay, so in order to get into just temperature here, we'll need to separate out our temperature gradient term. So also, we could say that since we have uniform conductivity, our heat flux will be some constant C. So to separate this out, we'll get on our left side negative thermal conductivity times 4 pi times our change in temperature is equal to our heat flux constant C divided by our radius squared times our change in radius. Okay, so currently we're taking the derivative of our temperature and radius terms. So in order to get into our units of temperature and radius, we'll have to integrate both sides. And we'll integrate with from our inner radius to our outer radius. So our temperature will be from the temperature of the inner surface. Our radius will be from the radius of the inner surface, and then all that to the outer surface. Okay. So with that, we'll get this. Negative thermal conductivity times 4 pi times our integral of our temperature derivative, which evaluated from the temperature of the outside surface to or temperature of the inside surface to the temperature of the outside surface, which we know will just end up being our temperature of the outside surface minus the temperature of our inside surface is equal to our heat flow constant C times 1 over our radius. So I'll just, which is evaluated from our outer radius, our inner radius to our outer radius. So what we're end up with is negative thermal conductivity times 4 pi times temperature of our outer surface minus the temperature of our inner surface is equal to our heat flow constant C times the reciprocal of our outer radius minus the reciprocal of our inner radius. So if we plug in all of our known variables, temperature of the outside surface is 0 degrees Celsius. Temperature of the inside surface is 100 degrees Celsius. Our inside radius will be 1 meter, and our outside radius is 2 meters. So what we're left with is negative 100 is equal to 1/2 C. So solving this, our heat flow constant C is equal to negative 200. And since C is our heat flow, we know that that is in joules per second. Okay, so now we'll pretty much repeat the same thing, but just for our midpoint. So starting out with our heat flow again, Fourier's law, which is our heat flow is equal to our negative thermal conductivity times our area, which in this case is 4 pi r squared, is equal to, times our temperature gradient, so change in temperature with respect to radius, is equal to our constant C, which we know is negative 200. Okay, so writing all this out. Separate our temperature from our radius again. We'll get our negative thermal conductivity times 4 pi times our change in temperature, which we will integrate again, is equal to is negative 200 over r squared times our change and times our change in radius. And for right now, we'll keep our negative 200 outside of the integral. So it'll be r squared. Yeah. So what we're left with, well, also too, now we will integrate from our inside surface to our midpoint. Okay, so this time I have negative thermal conductivity, 4 pi, is equal, times what we know will be temperature of the midpoint minus the temperature of the inner surface is equal to our heat flux of negative 200 joules per second times our negative reciprocal of our radius evaluated from our inside radius to the radius of the midpoint. So which will have our midpoint. So the reciprocal of our inside radius minus the reciprocal of our radius at the midpoint times -200. Okay. So we'll move our thermal conductivity term to our right side. Should be the inside temperature. Oops. -200 divided by our thermal conductivity times 4 pi. Okay. Yep. Okay. So plugging in all of our variables, or here, let's get this in just the temperature of our midpoint to begin with. So we will have our negative temperature of the midpoint is equal to 1 over our inside radius times minus 1 over our outside radius times -200 joules per second divided by our thermal conductivity times 4 pi minus the temperature at the inside radius. Okay, so now plugging in all of our knowns, we'll get the negative temperature at our midpoint is equal to 1 over, let me just write all this out a million times. It's equal to 1 over the radius of our inside surface. So that is 1 meter minus the reciprocal of our radius at the midpoint. So that would be 1.5 meters times our negative thermal conductivity, 200 joules per second over our thermal conductivity times 4 pi minus the temperature of the inside surface, which is 100 degrees Celsius. Okay, I'm realizing I messed up. This will be 1 over the reciprocal of our midpoint, so 1.5 meters. The reciprocal of our midpoint minus the reciprocal at the inner surface, so so yeah, if we plug this all in the calculator, we will get the temperature at our midpoint is equal to negative 33.3